In our previous video, we talked about, is the reaction going to happen or is it not going to happen? Okay, and in this video, we're going to talk about, okay, if the reaction's going to happen, we know that there are 4 different things that affect how fast or slow that reaction's going to go. And the 4 things that affect it are concentration, temperature, surface area, and catalyst. So let's start with concentration. When you increase the concentration of the reactants, and how do you do that? You put more of the reactants in there, okay? And at the same space, so the volume has stayed the same. What that does is, of course, it causes the particles to collide more frequently. They're hitting each other more often. And as they hit each other more often, of course, that's going to make the reaction go faster. Okay, and this can also happen if by taking the volume of the container without adding more of the reactants, simply by reducing the volume of the container. If you reduce the volume, of course, there's less space for those particles to move around in. So reducing the volume increases the pressure, which again causes the particles to collide more often. So not only do we need to know, yes, concentration is one of the things that makes the reaction go faster. Why does concentration make it go faster? Because again, the particles collide with each other more frequently. Okay, the second thing that causes a reaction to go faster or slower is the temperature. When you increase the temperature, so a rise in the temperature will obviously cause the reaction to go faster. Okay, one of the ways that they like to ask questions about temperature is by using what's called a Maxwell-Boltzmann distribution plot of energies. Okay, and it looks like this. Okay, and as you can see, let's make sure we understand this. So the left-hand side here shows basically the number of molecules. Okay, and then on the bottom here is the kinetic energy, which we know is directly proportional to the temperature. It could be either one of those. Okay, so when you raise the temperature, okay, when you raise the temperature, the red line here represents the higher temperature. And as you can see, what happens here is that when you have these 2 different curves, notice at the lower temperature, you have more molecules. Notice the height of that peak. You have more molecules with less kinetic energy. That's what that represents. Okay, and also notice that this line here, sometimes they put that line in there to represent, basically that's what we call the activation energy barrier. Remember when we had those curves like this, okay? To get to here, that's what this line here is representing, okay? That line is here. Okay, and notice at the lower temperature, there's less molecules. There's still some molecules can still make it over that activation energy barrier, but notice that it's less. Okay, at the higher temperature, notice that there is a greater number. Notice the kinetic energy, okay, is higher. That as that temperature goes up, that the molecules have more kinetic energy. And also notice that they have, again, from here all the way down, you have a greater fraction of molecules that have enough energy to overcome the activation energy barrier. Okay, so when the temperature changes, like if we were to draw on here, let's raise the temperature even more. What does the curve look like at even a higher temperature? It gets lower, and the peak moves over to the right a little bit farther. So it's going to be a little bit lower. And again, this is not perfect. Okay, but let's say something like that. Okay, so that curve right there represents an even higher temperature than our high temperature there. And again, notice we now have even more molecules that have enough energy to overcome the activation energy barrier. Oops, I'm going to erase that whole thing there. Oh, that one's even better, actually. Okay, what if the temperature got even lower? Then what would it look like? Again, the lower it gets, the more this peak gets taller, and the farther to the left it becomes, okay? And again, not perfect, but again, that's an even lower temperature. So the lower the temperature gets, the more it moves left and the taller it gets. And again, that just shows you have an even greater fraction of molecules that have less kinetic energy And again, you have even less molecules that have enough energy to overcome the activation energy barrier. Okay, now some of the other ways that they draw these. Let's just focus on the red one for right now, okay? What if you took that same gas at that same temperature, but now you have less of those gas particles? Okay, what you might see is something like this, where it looks almost exactly the same, but the curve's just a little bit lower. Okay, what if you have a very similar gas, similar in its molar mass and everything, but if it has a lower molar mass, okay, then you might just see a curve that looks, it might just go a little bit, same height and everything, but it might be a little bit more to the right. Okay, typically when you see one of these graphs, it's about temperature, okay? And we already saw at the higher temperature, it's going to look something more like this. It's going to be lower and it's going to be farther to the right. At a lower temperature, it's going to be higher and it's going to be much, much farther to the left. And again, I'm trying to get that line even lower, okay? Because the lower and lower you get, fewer and fewer molecules have enough energy to overcome the activation energy barrier. Okay, so now why does this happen? Again, because at higher temperatures, you've increased the kinetic energy of the molecules. And so when you do that, you've got, again, the energy of the molecules is greater, and that means a greater number of molecules will have enough energy to overcome that activation energy barrier. Okay, or another way of saying it, the red area to the right of that activation energy is larger than that of the blue area. Again, simply because you've got more energy in those particles. Okay, and a reaction will always be faster at a higher temperature because, again, more particles, not all of them, but more particles possess that required minimum activation energy in order to produce the products. Now, again, let's talk about why. What's the why behind this? Why does that happen? Why is it, okay, they have more energy, great, who cares? Well, when they have more energy, there's two things that happen. Just like when you increase the concentration or decrease the volume, we know that that makes the reaction go faster because the concentration is greater. We already talked about that. Okay, and why does that happen? Well, of course, because the molecules collide more frequently. Well, if they have a greater kinetic energy, the particles are moving faster. And here's the two important ones here. The collisions occur more frequently, so they're hitting each other more often. And when they do hit each other, because they have more energy, they're hitting each other with more force. Okay, that's two things you need to know there. Okay, so at a greater temperature, they're moving faster. So when they hit each other, they're hitting more frequently, and they're hitting each other with more force. And again, that makes it so there's a greater fraction of molecules have enough energy to overcome that activation energy barrier, which makes the reaction go faster, which makes the rate of the reaction increase. Okay, the third one, and that second one, that's the big one right there. That second one about temperature and being able to interpret a Maxwell-Boltzmann graph, that's the big one there. Okay, the third one, solid particle size or surface area. So when a solid reacts, only the particles on the surface of the solid are available for reaction. So when you break up a solid into smaller pieces, you've increased the surface area and more particles are available for collision. Okay, so again, what's the important part there? The greater the surface area, the faster that reaction is going to go. Okay, and why? The why part is because more particles are available for collision. Okay, so the greater the surface area, the more particles that are available for a collision, the faster the reaction is going to go. Okay, and we see that. I mean, even when you take, take ice, for example. You put one large block of ice into your water, it takes a long time for all of that ice to melt. But if you put a bunch of tiny little pieces of ice, like from Dairy Queen or Sonic or something like that, that ice melts much, much quicker and keeps your drink colder, because when you have a whole bunch of little tiny pieces of ice, you have a huge surface area compared to just a block of ice that the only ice that's available is the ice that's on the outside. That's a pretty good example right there. You're welcome. Okay, and now the last one there is what are called catalysts. And we're going to talk about catalysts later on in this unit. But just for right now, know that the 4 things are concentration, temperature, solid particle size, or surface area is easier, and catalysts, okay? And what catalysts do is, again, they make reactions go faster. And the way that they do that is they provide an alternate reaction pathway with a lower activation energy. That we're going to talk about later on, okay? But again, that's the way that catalysts work, is they provide a different or an alternate reaction pathway, and that pathway will have a lower activation energy. So in summary, 4 factors that affect the rate of a chemical reaction: concentration, temperature, surface area, and catalysts. Okay, and really, if you think about that, notice that all 4 of these factors relate back to the 3 factors that determine whether the reaction is going to happen or not. Okay, it all comes back to, do they collide? Do they collide with the right orientation? And do they have enough energy to overcome the activation energy barrier? Those are our 3. Is the reaction going to happen? And then when we talk about what makes the reaction go faster, concentration, temperature, surface area, and catalysts, those 4 are all dependent on really those first 3. And don't worry, this is not the end of any of this. We're going to continue talking about all of these. So here's a question again. This was back in Unit 3. I just wanted to go over it with you again just to make sure we understand that when you change the concentration, you go from 0.5 molar to 2 molar. Does the activation energy of the reaction, is it greater than, less than, or the same as when you're at a different concentration? Okay, and we know that it is the same. Okay, and again, you could say because concentration does not affect the activation energy. And don't write it like that. Write out activation energy. Okay, so activation energy does not change with concentration. A change in the temperature, again, which they don't mention here, but you really need to be familiar with. Remember that when you change the temperature, that also does not change the activation energy. And again, I bring this up because this was a question on the AP test. And they asked, and a lot of students talked about how when you raise the temperature, that you're lowering or raising the activation energy. That is not true. Okay? A greater temperature makes the molecules have more energy so they can overcome the activation energy barrier, but a change in the temperature does not change the activation energy. That's that wall that's there, and you have to get through that. You have to have enough energy to get over it. And if you don't, then you can't. And when you raise the temperature, more of those particles have enough energy to jump over that wall and get past that activation energy barrier. Again, the only thing that affects activation energy, which again, we'll get into more detail later on, is a catalyst, okay? And how does it do it? Again, by providing that alternate reaction pathway, okay? But a change in concentration, a change in the temperature, and even a change, again, think about all the other 3 of them. The surface area, the temperature, and concentration do not change the activation energy. They just either allow the particles to have more energy to get over that activation energy barrier or not. All right, there are some problems, some homework problems to work on now, and then in our next video, we're going to talk about actually calculating the speed or the rate of a reaction.